Hey everybody, welcome back. We're in 15.5 for Calculus 3, where we're looking at surface integrals. In this section, we've been looking at where one variable is a function of the other. And now we've got a surface that it's broken up into pieces. This will be our last example for this video section. So let's just look at our surface. It's a section of a cylinder. So we've got this pipe going up and down along the z-axis. It's cut off at z equals 0 along the bottom. There is a diagonal cut along 1 plus x for z. And the pipe is got a radius of 1. So I drew the picture. I'm going to label the side of the pipe S1, the bottom of the pipe S2, or the bottom of our shape, and then the diagonal surface as S3. So that's our surface. I chose to use, instead of doing x coming towards us and y, z being the plane, since z was a function of x, I chose to use that as how I mapped it. And I just got to make sure y is the positive section. This is the positive x, this is the positive z. The positive section of y has got to be backwards. I chose to draw the diagonal this way, just so it wouldn't be like this way where it's underneath the image. So it's the angle I chose to show it at. So we're looking at S1 and S2, and in fact, they're all going to be good in cylindrical. But several things are constant for, or not several things. Some things are constant for S1 and S2. For S1, the radius, the side of the pipe, it has a constant value for the radius. It's 1. And the bottom surface has a constant value of z equaling 0. We'll take advantage of that. We just need to do this integral for each piece, because S should be S1 plus S2 plus S3. So we got to find each value. Let's just jump into them. Let's go in order. So let's do S1 first. S1 is R is constant. And so what we really have is a function of theta and z. So x equals r cosine theta, r is 1, x equals cosine theta, y equals sine theta, and z, that'll be our surface. We've got 0 is less than theta is less than 2 pi, and 0 is less than z, less than 1 plus x. We're switching over to theta and z, so 1 plus x is 1 plus cosine theta. We need to find our RU cross RB, in this case, R theta cross RZ. So I took the derivatives and I set it up, and I got cosine theta, sine theta, and 0 for my cross product, which means the magnitude of the cross product is 1. So we're ready to set up our integral. We are doing ZDS. Let's not forget that. So Z for setting up, Z is what we're integrating. It's one of our variables. So we're going from 0 to 2 pi on theta, as we showed here, 0 to 1 plus cosine theta for Z. And we have dz d theta. There's a 1 in there. I didn't show it. I should have. Because it's important to note that goes in there. So times 1. But we know that doesn't change the outcome. So I integrate with respect to z. We've got 1/2 z squared, evaluated those values. We're going to get a little bit of trig going on. So we got 1/2 plus cosine theta plus 1/2 cosine squared theta. Again, we're going back to that cosine 2 theta formula. Make the substitution. So I replace cosine squared theta with 1/2 times that. So we've got this 1/2 times that 1/2 gives us 1/4. So 1/4 plus 1/4 cosine 2 theta. So we integrate that, and we're going to get 3 pi over 2 when we're done. So that is the side of our, that's S1. So we still need to do the bottom and we need to do the top. Okay. So along the bottom, remember the integral is z ds, but on the bottom z equals 0. So the what this contributes to the surface area with this function, I guess it's not just surface area. It's a, I know it's not just surface area. Surface area would have a 1 here. We're looking at it as a function of z. This contributes 0 to it. So finally, we have that diagonal surface here, where it looks like z is a function of, oh, I don't know. Let's maybe we shouldn't do z as a, let's take a look at how we're going to do it. Let's leave it as x and y because it's tricky. I don't want to try to interpret polar yet. Let's do x and y. So our derivative r with respect to x, derivative r with respect to y. We know that surface is z equals 1 plus x or x plus 1. So we find our rx cross ry, take the magnitude and we get root 2. So I can write it like this. Now we're looking at this. Basically, this has been mapped down to the dx, dy, or the x and y plane. The way we did it here, this dealt with the z. Okay. Now that we are in the xy plane, maybe I'll put it like this so we can see it. Now that we're in the xy plane, I can switch to polar easier. So let's switch to polar. Down there, we're doing, it's the whole surface now right there. So r is not constant. So polar is going to be rd theta. That is switching dx dy over to rd, over to dr and d theta. We know that conversion rate already. We don't need to do this again. And so our limits of integration will be 0 to 2 pi for theta, 0 to 1 for r. And we still have our root 2, that this is dealing with the z. Okay. So switched everything over. We had 1 plus x, now 1 plus r cosine theta. And we start solving. Distribute that r, factor out the square root of 2. It's actually straightforward from here. No tricky things. And you should get 3/2 plus square root of 2, all of that times pi. When you add up all of them, the top surface is just pi root 2. Okay, we add them all up, we get this value. It's not the surface area, it's the, I don't want to say density, but it's the value of the integral. Let's just say the value of the integral, because we had s was the integral. Wow, I should make that look more like an s, was z ds. So this z is throwing everything off. That's it for 15.5. Peace.